The interesting part of blockchain technology isn't so much the database itself, but rather how the same database can be used by a network of strangers who don't trust each other. Without a central authority, this isn't an easy task. To achieve it, blockchain networks rely heavily on a mix of game theory and cryptography. In this module, we're going to take a deeper dive into those mechanisms. It wouldn't make much sense for your bank to have a public document detailing every transaction between users. Due to their centralized client-server model, they can validate transactions in private. A blockchain, though, is a public database. Everyone needs to be able to look at a transaction and say with certainty that it's valid. If someone adds data that says, Alice gives 50,000 coins to Bob, how can we tell that Alice actually authorized the transaction? Who's to say that Bob didn't just add it himself? Maybe you could have some kind of password system, but that gives you two options. Either you use a centralized entity to check them, or Alice publishes her password for every transaction. The former doesn't work in a decentralized setting. You might as well just use a regular database. The latter doesn't work because everyone would know Alice's password. After her first transaction, anyone can make a transaction masquerading as her. To get around this, we use some cryptography, which involves the transformation of data for the purposes of secure communication. Even if an adversary intercepts a message from Alice to Bob, they won't be able to decipher it without a special key. Something like the Vignere cipher is what we call symmetric encryption. For example, we can use the key HODL to transform our plain text into ciphertext. It's not impossible, but it'll be time-consuming for an adversary to figure out what the plain text is without knowing the key. However, if we give someone the key we use to encrypt the message, they can use it to decrypt it. That's why it's symmetric. The same key is used to encrypt and decrypt. The thing we're interested in here is public key cryptography, in which you use a pair of keys, a private key that you keep secret, and a public key that you can share. Both keys are linked, so by using your private key, you can easily generate the corresponding public key. But this only goes one way. It's virtually impossible for someone to take a public key and reverse engineer it to get the private key. Therefore, there's no security risk to you sharing the public key. In fact, you need to share it to make transactions. Private key holders can write a message and digitally sign it using their private key. By comparing a public key with the signature, you can safely assume that the person who owns the private key has written the message. This is an important building block in blockchain systems. The private key acts like a password, or rather an identity, generated mathematically. By using your private key to sign a message, you certify that you're not authorizing an action. That's why you should never share it. Anyone who knows your private key can produce a valid signature to spend your money or otherwise impersonate you. In a nutshell, blocks are made up of messages that say something like, I, Alice, pay 50,000 coins to Bob, and here is my signature to prove I authorized this transaction. That message gets passed around the peer-to-peer network as users check that the signature matches Alice's public key. If it doesn't, they'll ignore it and the transaction won't get validated. So, we figured out how to stop people from spending Alice's funds. What we haven't figured out is how to prevent Alice from spending the same funds twice. How do we decide which transaction to include in the blockchain? Who decides? How do we reach a consensus decision in a distributed system? We will answer these questions in the next module.